Okay, hello. This is the first lecture and introduction to ETEC3402, Automata and Formal Languages. And this is going to be divided up into two videos. They'll both kind of have links on the course page. So look for those. And the reason that we're doing this over video is that I had a COVID breakthrough infection. And I'm almost back to normal, but I'm still, maybe you can hear, I'm still a little symptomatic. So for the most part this semester, we're going to have face-to-face lectures, traditional lecture format. But initially, we are going to have a couple, maybe one, maybe two video lecture periods. So make sure to keep up with those. Make sure to look out for that. So today what we're going to do, let's go ahead and go through just a couple quick things here today. And the reason I'm doing this rather than just not having class at first week is I really don't want to get behind on what we're doing this semester. So let's go ahead and dig into it a little bit. So what we're going to do today is talk about the syllabus, talk about my teaching philosophy for this class, which could be useful for you to understand, and then also talk about a little bit about the subject matter at hand, which is automata and formal languages. So let's go ahead and get started. All right, so first off, course expectations. Let's first look at the syllabus, and there are going to be a few things that I'm going to mention that are different. A lot of you have had me for classes before, so I'm not going to spend a whole lot of time on that. I don't think there's a lot of reason to spend a lot of time on going through that. You can always read through it at your leisure if you want. So let's go ahead and take a look at that. So let me switch over so we can see the syllabus here. So give me just a second. And all right, so there's the syllabus. So first off, we are going to meet in person primarily throughout the semester. Monday and Wednesday, 2 to 4:15. We'll probably do about an hour of lecture, take a 5-minute break to use the restroom, and then get back to it and finish things up. So that break, there'll usually be a break partway through. Some days though, we might have so much to cover, we get started and rolling. So just come prepared for lecture. Now this class is in 326 Advanced Technology Center. You should have that on your schedules and be aware of that. Now, if you do need help for office hours will be held face-to-face or by appointment. So it is totally possible for you to make an appointment that's outside of my normal office hours, and I can set up a Zoom meeting or make an appointment during my regular office hours, and we can do that by Zoom, or you can come in and see me. The times are listed here, essentially 1:30 to 2, Tuesday and Thursday, and then Monday through Thursday is a larger block of time, 4:15 to 5 o'clock. So in other words, right after class on Monday and Wednesday, I'm available. So make sure if you have questions, if you're struggling with anything, make sure to come by and talk to me. And my office is in 307 in the ATC building, same floor, right down the hallway from where the class meets. So after class, probably the easiest time to get a hold of me. But if you're doing homework at other times and need help with something, let me know. Also, feel free to email me. I have both my Gmail address and my university email address listed here. Either of those would work. I would prefer you use the university one. The university said they would prefer that we do all communication through the Shawnee system. But if you have something that's urgent, you might email me at both of these because I get the Gmail one more often than the university one. All right, a couple of notes about office hours. I am available for face-to-face meetings, but at the times listed above. But if I'm not, my schedule doesn't synchronize with yours, just let me know. I only live a block from the university. I'm happy to come in on evenings or weekends or whatever, within reason, obviously. And just let me know, and I will get back to you and we'll set something up, or just show up at office hours and I'll be there. All right, there's no textbook for this class. There are some books I would suggest that are useful if you want to study further or feel like that would help you to have a book to read through. Just let me know and I can recommend it. But all of the material we're going to cover is going to be provided in the class in the form of lectures. Attendance, there's no attendance policy. there's the grading system. Only important note on this, if you haven't had my classes before, you have to pass the final exam to pass the class. Also in this class, one thing that's going to be a little bit different is normally in classes like this, there are programming assignments. In Automata and Formal Languages, it's more going to be homework and quizzes. So there are going to be a lot of quizzes, and their homework is, instead of programming related, it's going to be working out things on paper. And that's just the nature of this class. This class is a little more theoretical than it is just a programming class. We will do some programming towards the latter part of the class to put what we're learning in here in practice. But there are going to be a lot of quizzes and the homework, less homework, but the homework assignments will generally be on paper, or you could type them out and submit them. But just keep that in mind. They'll end up being about one quiz per week, actually. But other than that, that's what the grading system looks like. You have to pass the final to pass the class. If you learn the material that we cover in here, it won't be particularly difficult. All right, don't cheat. In other words, when you do your homework, it's okay to talk to other people and talk it over with other people. Make sure you don't just copy what somebody else has and turn it in. It's okay to have study groups and okay to kind of discuss things, but make sure what you turn in is your work. And make sure that you understand what it is that you've turned in as well. And also, that's probably the best way. The homework is, and the understanding what you did on the quizzes is going to be your best way to make sure you're prepared for the exams in the class as well. All right, programming assignments. There's a bunch of stuff about programming assignments, but they're not really, there aren't going to be that many of them in this class. But notice with other assignments that these rules still follow. So in other words, turning something in, you should submit it on the Blackboard page. Don't just email it to my email address and expect that I'm going to get it without some prior arrangement. Don't print it out on paper and slide it under my office door. For the written assignments in here, I will accept them being turned in on paper. If you want to fill them in on paper and hand it in, sometimes that can be easier for you than having to try to type out something that's more of a drawing. So either on paper, turned in class time, or turned in on Blackboard. Either of those is good. All right, exams and quizzes, we already mentioned that. The ADA statement, if you do have some sort of accommodation need, make sure to work through the Office of Accessibility Services to get that handled. In other words, you want to, maybe you need have a accommodation where you need to have the tests printed off in a larger font, or maybe you have a accommodation where you need to take the exam in a quiet place or something like that. Work through that Office of Accessibility Services, and then make sure before those exams to talk to me about that and communicate that need with me as well. And I'll work with you on that as long as you work through that Office of Accessibility Services. In other words, don't wait until the day of the exam and then say, oh, by the way, I need this done immediately. Just make sure to let me know ahead of time so we can all be prepared. There aren't any last minute racing around trying to make those accommodations. The Title IX statement is on there as well. You can read through that if you want. And I also, for convenience, provide the phone number for the Title IX coordinator. So if you need to report some sort of an incident, make sure to do that formally. In other words, we don't want anybody to feel uncomfortable or anybody to feel harassed or anything like that. So if you do have some incident or you see something, say something. We want to make sure we maintain that healthy academic environment for everybody. And other than that, that's it for the syllabus. One thing I did skip over was the description of the class. So let's rewind to that for just a second, and let's read through that together. All right, so this course description, again, the course itself is called Automata and Formal Languages. And like I said, this class is going to be a little bit different than some of the other classes you've had with me. For example, if you had me for systems programming, we did a lot with a programming language, kind of lower level stuff. You wrote code, you compiled things, you ran those things. This class is more of a theoretical computer science class, although I'm going to teach it a little differently than if you had this, for example, in a graduate school environment. I'm going to teach this class with in a way where we're going to learn the theory, but we're also going to look at what you can do with that, or what power it gives you. How can you solve problems with the things we're going to learn? And let's read through the course description. So it says, the study of formal models of computation in terms of abstract language and machine models. And let me editorialize for a second. Notice the word abstract language and machine models. Notice that word abstract there. So this is not a programming languages class. This is not a class where we're going to learn a new programming language or an SDK in a programming language that does something. All right, so continuing on, it says these include formal languages, finite state automata, push-down automata, Turing machines, and grammars. This course provides an introduction to the theory of computation, focusing on the fundamental relationships between various abstract, there's the word abstract again, computing models for certain formal languages. The fundamentals of computation, complexity, and computability are studied in terms of these abstract language and machine models. Many of these concepts become of fundamental importance in other areas of computing, such as compiler design, computer architecture, object-oriented design, computational linguistics, and artificial intelligence. And then it goes into the list of topics, which I'm not going to read through right now because those aren't going to make a whole lot of sense. But the last sentence there says, lab emphasis is upon applying the concepts to various aspects of computer hardware and software development and problem solving. And so this class, to me, we'll get into the actual material here today as well. But this class, to me, is a chance to take a computer science subject and then see where you can use the power of these things. And we're fortunate to be living when we are, that a lot of this abstract work has been done already by others. And so now we can take advantage of that. And solving certain kinds of problems, this gives us a whole set of really powerful tools that if we didn't have in our toolbox, it would be really difficult to solve those problems. And notice in this list of applications here, like computer hardware development, software development. Those are things that if you're in one of the CET degree or the gaming degree, those are things you should be interested in. Problem solving, but also up here, it mentioned the list of things like compiler design. Writing a compiler without a theoretical understanding of the topics we're going to talk about in here would be really challenging, and it's unlikely you would be successful. But using the stuff we're going to study in here, that's going to become much easier to do. And we'll get into that here in a little bit. So let's go and switch back to the presentation, and let's make a quick take a quick look at some things that we're going to look at in this class. So before we do that, however, my teaching philosophy, the verb phrase to teach, doesn't make much sense. And if you've had my classes before, you'll know that, because I expect you to be the active part in that, not me. So for example, to hit, yeah, that makes sense. Or to toss, I can throw this thing in the air, I can tap it, I can bite it. So all of those, the thing is passive. But to teach, I can't really teach you things without you being an active participant in it. So you need to take it upon yourself that if you're not understanding stuff, ask questions. And when we are face-to-face, the class is going to be somewhat conversational, somewhat lecture where I go through things. I'm going to involve you in that conversation, and I want you to try to take an active role in that. If you're not understanding something, chances are somebody else probably isn't either. Ask a question. Raise your hand, ask a question, we'll discuss the question you have. And a lot of times I'll ask questions in class, participate. It'll be more fun, you'll be more active, it'll be more engaging, and you'll learn better that way. Okay, so automata and formal languages. What is it and why study it? Well, let's go through that quickly here. So to start off with, what is it? Well, if you look up the word automata in the dictionary, as you can see here, it says it's the plural of automaton. So what is an automaton? It's a moving, and this is from the dictionary, look up for that. It says it's a moving mechanical device made in imitation of a human being. So a machine that performs a function according to a predetermined set of coded instructions, especially when capable of a range of programmed responses to different circumstances. And It also says it's used in similes and comparisons to refer to a person who seems to act in a mechanical or unemotional way. And those aren't exactly the definition for what we're going to use in this class, but it does convey something. It's something that's a machine that moves in a mechanical way. Or also a person that maybe acts like one of those machines that does that. So if somebody is an automaton, they're kind of like a robot that has this pre-programmed way that they do things and go about things. Or if you have an automaton, there are some famous examples of automatons are things like those clocks that have the little guys that come out and they raise the trumpet to their mouth and they like dance around in a circle. And if you've ever been to I don't know, something like Disney World's Small World ride. That's the kind of thing where those things are automatons. They do a sequence of things that are predetermined. Now, in this class, we're really more concerned with automata and an automaton being kind of a mathematical model for that. So here's from Wikipedia. Wikipedia says, automata theory is the study of abstract machines and automata, which seems a little self-referential, as well as the computational problems that can be solved using them. It is a theory in theoretical computer science. The word automata, the plural of automaton, comes from the Greek automata, meaning self-making. So, in other words, notice that this is the study of abstract machines that is a theoretical field of computer science. And you also notice that below that it says automata theory is closely related to formal language theory, and automaton is a finite representation of a formal language that may be an infinite set. Automata are often classified by the class of formal languages they can recognize, typically illustrated by the Chomsky hierarchy, which describes the relations between various languages and kinds of formalized logics. Automata play a major role in theory of computation, compiler construction, artificial intelligence, parsing, and formal verification. And again, one of the things that we're going to focus on is the formal part of this, the theoretical abstract parts of it, and understanding that. But then we're also going to look at the role it can play in you having extra tools in your toolbox to do things that you otherwise wouldn't know how to do. So this is going to be a class. And I have to say, from my experience, this is one of the classes that I had. I didn't have automata when I was an undergrad. I had an automata for the first time when I was in graduate school. And it was one of those classes where the way it was taught to me, it was almost entirely theoretical. But even then, I recognized the power of what we were learning. And it has transformed the way I approach problems, both with hardware design, embedded systems, and a whole range of other things, software engineering. There are problems that you can solve by the tools that you're going to get, the techniques we're going to use in here that would be difficult to solve otherwise. Okay, so why study it? Well, let's take a look at that. So computer science and computer engineering are largely considered to be practical disciplines. In other words, you're using a computer to solve some sort of a problem. And you see that with writing code for a game or building some embedded system to do something. Either some problem, you build the system, write the code that then breathes life into that system to solve some problem. Maybe in gaming, it would be solving the problem of network communication between the different players on a multiplayer game. Or maybe it would be creating some sort of a model for weather, so there's dynamic weather in your game system where clouds can roll in, rain can start, or maybe it's something creating the model for the motion of the waves, and you need to write the code to do that. So in a lot of cases, though, computer science and computer engineering are practical. You're using a computer to solve things. So why would we ever solve or study anything that involves theoretical when we could just like hack together some code? So let's take a quick look at that. So why study automata and formal languages? So why would we ever study theory? And the answer to that is that I've encountered people that have these two extreme views, neither of which I think are helpful or productive. The first one is what I would call the hacker/programmer view. They're like, the theoretical stuff is useless. If you just need something, you just hack together some code. If you want to see if your code works, you just run the code and see if it works and test it. So throw all of the theory out the window and you just, okay, I have a problem. I'm going to bang together some code and then see what happens. If it works, then great. If it doesn't, then I'll fix it. So that's one view, which is flawed, and we'll talk about that in a second. The other one is more of the computer science formalist view, where they say that every algorithm and every system has to have some formal underpinning that's based in some sort of proof, and you need to do that in order to have your code considered correct. Or maybe you even need to do that with your algorithm before you ever write the code and test it. You need to formally prove that your code is correct and complete, and you should do that before you write the code or before it would ever be considered correct. And I don't think either of those is a good viewpoint. I run into a lot of hacker/programmer types, and their view is, theory's stupid. I'm not going to study that. I'm just going to bang some code together. And the CS formalist views are like, oh, I don't want to write code. I want to prove things. And neither of those is really a good balance. So, for example, if we were to apply that same viewpoint to, I don't know, let's say something like building a bridge or designing a bridge, the hacker view would be like, all this math is for nerds. Let's just start putting some steel together and then drive some cars over it and see if it stands up or not. And while that might be an approach that could work, it also means that if you don't have the theoretical underpinning to do the math, to know the stresses and strains, you could be designing something that is dangerous and will collapse. Or conversely, you could say, well, I'll just over-engineer it to make sure it doesn't. You could be designing something that is wasteful and has too much stuff in it, more than it needs, and it's going to suffer budget-wise because you don't know where the point is that gives you the amount of strength that is required for that task. And the other thing is the hacker view is something like building a bridge. You might start building something and then the whole thing just won't work right because you didn't do the math right and you didn't know how to measure things and you didn't know how to do the statics and strengths calculations. And then the formalist view is also flawed. And if you think about it there, maybe they draw out the bridge on paper and they do all these things, but there are also real world conditions that come into play with how long do you have to complete the project. And maybe you don't have to do the full bridge design every time. You can reuse a design that's already done previously, rather than for every time you do something, you have to prove the entire thing. So that there are extremes there that we want to avoid. We want to have something that's a little more balanced. So what we're going to do is we're going to look at the theoretical side of this, but also we're going to spend some time talking about the practical side of it. And the nice thing about automata and formal languages is it really touches almost every discipline in computing. So for example, hardware design. You're designing a circuit, or you're designing a microprocessor itself. You're doing the VLSI design work down at the gate level, or you're designing a system that needs to be redundant for, I don't know, some sort of spacecraft that you're designing. Automata and formal languages can help with that. So chip design, embedded system design, computer architecture. And also, if you're programming things and you need to communicate between one system and another one, the design of protocols. How do you start the connection? How do you maintain the connection? How do you make sure it's reliable? So all of that comes into play with code that needs to communicate. And it could be simple communication with one chip and another chip on an embedded system, but it could also be something that's on a network. So that protocol design can benefit tremendously from understanding theoretical things about automata and formal languages. And then obviously applications themselves. We already mentioned compiler design and artificial intelligence, to name a few, but also really programming things. Concurrent programming can benefit from understanding the stuff we're going to talk about in here. So there are a whole lot of applications there, and we're going to look at those in this class. So to summarize that, the advantage of studying the theory or theoretical abstract concepts is that each of those subdisciplines of computer science and computer engineering have commonalities. Each of those, even though you might look at this and say, well, hardware design is completely different than writing a program, it's really not. There's some common shared traits there. And so by understanding and studying those common underlying principles like that, that really gives us a way to study those principles in an abstract way and then construct models that apply to those abstractions. But then by just the nature of it, you can apply that to any problem or any sub area that you're looking at. So some of those things will universally apply. And so there's great power to that ability to, how would I say it, like manipulate things in a theoretical way that kind of like algebra. Algebra is not just useful for doing, or calculus is not just useful for doing physics calculations. It can be useful for all kinds of things, financial calculations. It could be useful for some sort of programming calculations. So think of this, which is really what it is. Automata and formal languages is really a branch of math. And the way I like to think about it, it's kind of like the math of patterns and machines or algorithms that manipulate those patterns, either generate things from patterns or recognize things from patterns. So automata is sort of and formal languages is like that mathematics of patterns. And again, there's great power to that. So the whole concept of theory and abstraction, that's going to give us tools to use that transcend certain implementations or programming languages or hardware. It's a tool that we could use in any programming language or any type of hardware that we're working with. Also, those universal tools are going to be able to be applied to a whole host of different problem domains, and we talked about that a little bit. And it's also going to give us ways of analyzing and classifying problems, and so that we can know what problem domain do they fall in. And that's where in the course description, there were different classes of language, like, for example, regular languages versus context-free languages. That can be important when we're designing a system to make sure that the types of patterns match the type of, that we want to recognize, match the type of machine or model we're using to try to represent or parse or create those things. And without the theory that underpins that, you would spend a lot of time trying to reinvent the wheel, and that's really just a path to misery. That, again, if you want to write your own programming language or your own compiler for a programming language and you didn't have any of this theoretical stuff from automata and formal language theory, you would spend a lot of time going the wrong way or doing things that were wrong, where these tools will be are very powerful and will lead you the right way, and you'll know that it's the right way, and you'll be able to convince yourself that it's the right way beforehand. All right, so what about the immediate applications? Well, here's a whole list of applications. Communication, we already talked about. The internet runs off of automata and formal languages. TCP/IP itself, the communication that you use over the internet, there's a finite state machine, which is a formal class of machine model that guides that. HTTP, how does your browser parse the data that comes in and know what's a tag and what's not, and what is grouped inside of what thing, and how do we lay the stuff out on the screen and render it based on that? Automata underpins that. So HTTP, HTML, both CSS, all of that stuff is basically patterns that need to be recognized. Automata is the thing that's underlying that. Compilers and interpreters. When you write a Python program and run it, how does the interpreter know how to interpret that? Formal languages help with that. If you have a virtual machine like for Java, there's a formal model that they use to describe how that behaves. Again, formal languages and automata underpin that. C compilers, really any type of compiler that you're using. If you're using a game engine and you're using C#, that's all automata and formal languages that underpin those languages. Natural language processing, like things like Siri and Alexa, or Bixby, S-Voice, whatever. Those are all underpinned by some sort of natural language processing system that is used as automata and formal languages in those theories in some way. Embedded systems, automotive systems, kind of application-specific embedded systems like for elevators or building automation or security systems, all automata-driven. Chip design itself, if you're going to design a CPU or optimize hardware or do very large-scale integration, kind of like the silicon that goes into chips, all of that underpinned by automata and formal languages. It's, again, patterns. That's patterns of transistors or gates hooked up with each other in some way. You can minimize that. You can manipulate that. You can optimize it, whatever you need to do. But that's still, there are patterns involved in that. Artificial intelligence, neural networks, fuzzy automata or fuzzy logic systems, genetic algorithms, state-based AI, all of those things, again, automata and formal languages underpin it. Computational biology, things with fractals in things like how plants grow, DNA, other natural process modeling, automata and formal languages fit into that. And then games, obviously, if you're dealing with AI, you might have non-player characters that take actions, or the game logic and sequencing itself, level mechanics, all of that can be underpinned by automata and formal languages. Okay, so to finish up, before we dig into the actual core of the material, I want to take a quick look at this handout that will show us some of the areas where automata and formal languages show up. And again, think about this like a theoretical math class where it's the mathematics of patterns and pattern processing and recognizing patterns. And because patterns are so common in computational tasks, search for this text, or find the open and close tag for this thing, or find the open curly brace and the corresponding curly brace that goes with that when you're parsing this. Parse this source code into a parse tree that embodies all of the ways that it's divided up with what's inside of this if, what's inside of a while, where does that while end, where does the if statement end, where does the function body end. Somewhere that's all patterns that have to be understood by a program, and that's where it helps. So let's take a quick look at this handout. So give me just a second to switch over to that handout here. And okay, so here's the handout. And first off, automata and compilers. Now, let's say here's a function that's being compiled. This is a simple string length function written in C. And you'll notice that looking at this code, for that to get turned into something the computer can run, it needs to go through and understand the pattern of characters that are here. Somehow it has to know that I and T space together makes the word, a keyword, int, which makes an integer variable. And then this is a variable name and the equal sign and the 0. How do you write the code so that it knows these patterns? How do you know that this is the while keyword and that it requires these parentheses afterward, and that asterisk here is a dereference operator is getting the thing pointed to by that pointer that was passed in? All of that has to be figured out by the computer. It has to compile this by parsing it and understanding it, and then creating the object code for that, or the resulting executable code. So that has to get turned into a pattern. So we're taking one pattern, have to break it down and understand it, and then turn it into another pattern. Let me zoom out so we can see both of those at the same time. So this is the source code. This is on some processor, what that compiles to. And this itself, this is actually assembly language, which itself has patterns in it. So the operator, the operands, something has to understand what those mean and then turn that into the machine code that underpins that. All patterns understand, and those patterns can be nested with, for example, this while loop inside of the function body, and we have to somehow make code that then fits that same thing. And you're going to be doing that a lot in the compiler class next semester. But again, compilers is one of those areas that is underpinned by automata. It's all patterns, figuring out the structure of these patterns and then turning it into this other pattern. All right, another one, automata in the printer. So if you're in the classroom and you're at home and you have a printer, that printer has to have some sort of language that gets sent to it that then tells it how to draw what it draws on the screen. One such standardized language is a language called Postscript, and this is actually Postscript code, what it looks like. You'll notice it's got patterns, it's got comments. The things with percent signs are comment lines. But then it also has these commands, the /box, and then notice there's a curly brace and a closed curly brace, and then there's this def thing at the end. But this is a language that prints stuff, and you'll notice down here, here's what the output looks like, the output target, that this stuff gets turned into this. So it has to interpret this pattern and understand it and produce this as a result. And there has to be code that does that, and that's where something like the automata and formal language stuff comes in. So if you were to send this Postscript program, you can think of it as a program, to your printer, this is what would pop out. Okay, integrated circuit design, VHDL, which VHDL is a definition language for creating these VLSI devices. And so you notice, like, here's the input source. It looks a lot like a programming language, but the output target ends up being a circuit that then you can put on a chip or build into a chip, and then the chip will do exactly what it is that it was created to do. But again, how do you interpret this? How do you understand what this means and these patterns when it's really just the source code for this is just like source code for a program. It's just a bunch of characters, but something has to know how to group those, how to interpret those, how to parse that and understand it and understand the structure of it to actually create that circuit like that. And then that would end up being targeted onto some chip like this. All right, automata in games. Here's a really old scripting language for the Quake games, but you have this stuff that looks like program code, and there has to be an interpreter that runs that understands what all of these different things mean. Again, it's just characters until it gets grouped and parsed and then understood. But what the result of this is, the target is this lightning gun, how it creates this firing pattern. And that's essentially what this code up here is doing, is that's the fire lightning function. Notice this kickback angle, the owner of the Thunderbolt flies straight on. There's a speed associated with it. It calls this lightning hit when it touches somebody. Disappears after flying for 5 seconds. So all of this stuff has to be understood and parsed into that behavior, that output. And that's true for other games as well. Like if you're using Unity and it has C# or you're using even something like the Unreal Engine with blueprints, how do those get understood by the machine? Automata and formal languages. Automata in your browser, you give this HTML that has to be parsed and understood. That here's where the body of the HTML is, and actually this is wrong the way that I have this here. I should fix that. There should not be nested like this. The body should be inside of the HTML. But anyway, this is what gets output on the screen. Here's another one, VRML, which is a VR modeling language for virtual reality. You define this stuff that creates this shape by saying, here's a shape that consists of these various parts. There's a cylinder, there's a sphere, and that creates this little UFO object that you could then move around in a VR environment. So rather than using an art tool to create this, you could do it all programmatic like this and then have that shape show up, including giving it colors or textures or whatever you want to do. And here's something similar, but for things that show up not in a virtual world, but in the real world. If you've ever used a 3D printer and printed stuff, One of the file formats you can use for that is STL, which is a stereolithography file format. But you'll notice here, here's a solid that I made that actually has these vertices, and it defines those, and that actually makes this cube. So there's a cube that I printed out on the 3D printer based on this file. So, but in order to turn this into that, something has to understand how to read this in and understand how to parse this and figure out the pattern of it. And you might think, well, I could hack something up that does that. But what if you have a more complicated object where it's not just a bunch of facets like this with the outer loop and then the end loop? What if it has, that loop has another thing inside of that and another thing inside of that? You have to be really careful about how you parse those things. All right, here's another one. We mentioned TCP/IP. Here's the state machine for TCP/IP, which is the communication protocol that underpins the entire internet. So you'll notice that we have the connection state can go from listening and they get these synchronous received, synchronous sent events. The connection can be established. And essentially the subsystem itself, when you have a connection, it goes through all of these little states. And this is notice that this acts as like its own little kind of abstract machine. If you follow the arrow and follow what's labeled on the arrows, it handles every possible case of what can happen in communication protocol. Where if you tried to just hack this up, there might be certain corner cases that get missed or certain things that are harder to understand. But being able to draw a model of it like this can be really important. All right, here's some automata in games. Here's one for Pac-Man. Similar to that, wanders the maze. If Pac-Man is spotted, you chase after them. If Pac-Man eats a power pellet, then the ghost flees. If they get eaten by Pac-Man, the little eyeballs return back to the home base. When they reach the central base, they go back to wandering again. And if the power pellet expires, they go back to wandering rather than fleeing. And you'll notice that this could be used to model how the ghosts behave in Pac-Man. And you could make this more complex. So you might have a non-player character AI that's more complex. Here's another simple one. You have the AI that they wander around. If the player gets near, they attack them. If the player goes out of sight, they go back to wandering. If they're attacking and the player is attacking back, then they try to evade. If their health points get low, then they, instead of just wandering aimlessly, they start looking to find a health kit. If the player is idle again, they go back to attacking. So they'll go back and forth. They evade when you attack when you're not attacking them, until their health gets low. Then they'll go off and run away from you and try to find aid rather than just dying. And so you could make these kinds of models like this really complicated. It might depend on their karma level versus yours. So for example, if they're a bad guy and you're a good guy, they might do something different when you interact with them. If you're bad and they're bad, they might try to talk to you and welcome you in. Or there are all kinds of complicated things we can make to model that kind of behavior, but it's useful to understand how to manipulate those models and how to set those up. All right, last few here. The CPU design itself. The CPU, when it runs code, you give it like, it's really, your programs are just a bunch of numbers like this stored in memory boxes. The output target is to understand how those are grouped, like the 53 is its instruction, the 83 is an instruction, but it has EC and 38 as sub parts of that instruction. How does all this get figured out? What's data for instructions? What's instructions? Well, the processor has a machine that knows how to process that, how to parse that, how to group those things and interpret it as this kind of set of behaviors. And this is kind of a finite state machine. You'll notice it starts up, has this instruction fetch that happens, then it decodes the instruction, and then it has different ways of carrying out each of those instructions. Once they're carried out, it eventually jumps back up to the top to fetch the next instruction. So fetch, decode, execute. and then back up and fetch, decode, execute. So when they designed your processor, they made this kind of formal model like this to model the behavior, and then they built the transistors or the logic gates into that processor to embody this. And actually, each of these sub-steps might have its own little machine that has part of it, that governs part of how it behaves. Okay, so that takes us to about the 45-minute mark here. Let's go back to the slides for just a second. So we looked at that handout, and I really want you to pay attention to the stuff in this class and not think, oh, this is theoretical, it's not going to be useful. Because I swear to you, of all of the classes I had, like for example, I took programming classes but I was already a programmer. I've been professionally writing code since high school. And so when I took programming classes, maybe they added some things I didn't know, or I thought about some things I wasn't aware of. And I had written really complicated parsing systems before I ever took Automata. But when I had taken Automata, it changed the way I looked about solving those problems. It gave me power that I didn't have before. And it was the kind of thing that I maybe wouldn't have stumbled onto on my own. I would have just kept hacking things up and taking a long time and having them sometimes fail, and then adding more hacks on top of something that didn't work. But Automata gives you a set of tools like, I don't know, imagine trying to build that bridge again without knowing how to do any math, or imagine even trying to do some simple things without knowing how to do basic math, or how would you ever send a moon or a rocket to the moon without being able to do math and physics? It'd be almost impossible. And the same thing is true for Automata and formal languages. Some tasks are really difficult, bordering on impossible to figure out without having these tools at your disposal. And the cool thing about this is those tools are so powerful that you can apply them to really almost any code you write, or any program you work on, or a hardware system you design. And so we're going to focus in this class on doing those theoretical things. We're going to get started here right after the break. But not only are we going to do that, I'm going to try to tie these things into some of those applications that we talked about earlier. So I'm going to try to tie this, the theory into, all right, now let's do some stuff with it. Let's parse some data. Let's write some code that does something useful with this stuff. And you're going to be using this stuff again next semester in the compiler class. Okay, so in short, if you plan on being a developer or an engineer, then learning this stuff that we're going to cover in this class will change the way you approach those problems. And that's true in a whole wide range of areas. And I'm going to try to connect the dots for you. We're going to do the theoretical work, but we're also going to do some practical things with that. All right, so enough of the Automata pep rally. Hopefully you feel like this is stuff. Well, the other thing about the stuff we're going to do here is it should be fun. The stuff we're going to do here, it's like little puzzles or little logic problems to solve. And so hopefully it ends up being both enlightening and fun, but at the end of the day, it will make, if you learn the stuff, I guarantee it'll make you a better programmer, a better engineer, a better developer, no matter what you're developing. So let's go ahead and get started. We're going to take a quick break, and then after the break, we're going to dig in. It's not all for today. That's all for right now. But we're going to dig in and actually go through some foundational material for Automata. So we're going to get started with a little bit of set theory stuff. So take 5 minutes, regroup, get a drink, and settle in, and then watch the second part of the video. And after that, that will be all for today. And keep in mind that even though today's class was through this lecture video, that's not going to be the case throughout the remainder of the semester. We're going to meet face-to-face. So be prepared, check your email, check the course page, because I'll make an announcement about whether Wednesday will be face-to-face. I think it will, but it depends on my symptoms. I'm still a little symptomatic. Technically, I think I could return based on CDC guidelines, but just to err on the side of caution, we're going to do these things through video till I feel like I no longer have symptoms. And one final note here before I let you loose on break. If you're not vaccinated, please get vaccinated. I was vaccinated and had a breakthrough infection, but the symptoms were much more mild than they would have been if I wasn't vaccinated. And it really doesn't make sense not to get vaccinated. Essentially, vaccines use your immune system. They're a way for your immune system to practice building antibodies and be ready for when the real thing happens. So it's a safe way to make sure your immune system is ready when it's go time if you get the real infection. And as an aside, there are now like a whole lot of people. What is it, like 460,000 people or whatever that are now not alive because their immune systems couldn't figure it out fast enough. So I want you guys to stay safe. I want you to make sure that the people in our community are safe. So please, if you're not vaccinated, get vaccinated. It's free. It's easy. It's not a big deal. And the more people that are vaccinated, the less likely this thing's going to keep getting passed around, and the less likely there are going to be even more dangerous variants or more variants that have a even higher R factor. So get vaccinated and stay safe around campus. All right, I'll see you in a couple minutes, and we're going to dig into some actual material today. So I'll see you in just a couple.